This lecture is on Chapter 2.4 to Chapter 2.7 on orbitals and quantum numbers. So the Bohr model treated electrons as if they are particles that are flowing throughout these well-defined orbitals. But are they really? So this is the underlying question that led to de Bruglier's hypothesis. So in 1924, Louis de Broglie suggested that if light can behave in some respects like matter, then perhaps matter can behave in some respects like light when we're dealing on the atomic scale. And so just like light has particle-wave duality, de Broglie wondered if matter can also have that particle-wave duality when you're on the atomic scale. So this theory states that electrons can behave as standing waves. And so a standing wave is a wave that does not move. It has a fixed amplitude. So you can think of it in terms of a guitar string. So when you pluck a guitar string, you'll see that this standing wave forms. The string itself never actually changes in position. It just begins to go in this sort of sinusoidal wave. And so the higher the frequency, or the higher the times per second, the difference, the tone or the pitch of the guitar string will actually make. And so that standing wave, you can actually watch this wave occur. And so the de Broglie hypothesis imagined an atom as a circular standing wave, where the electrons exist as waves surrounding the nucleus with areas of high and low probability of where the electron is actually able to reside. And so when we think of a standing wave, the areas that are far away from the central line in the middle were our area of high probability of finding an electrode. And this area here in the middle of the wave, where the wave kind of centers around, which are called nodes, a point in the wave where the amplitude is zero, those are areas with zero probability of finding an electron. De Bruglier's hypothesis led to work in 1927 by Werner Heisenberg in the establishment of the Heisenberg uncertainty principle. So Heisenberg stated that due to the wave-like behavior, it is impossible to know both the position of a small particle and what path that particle follows. And so that statement is called the Heisenberg uncertainty principle. And so this directly relates to the impossibly small electron within the atom. And so this YouTube video is a very interesting sort of illustration of the Heisenberg uncertainty principle, and I very highly recommend that you watch. And so if we're unable to know both the position and the path of an electron, how do we know where these electrons actually are? And so the answer to this question is quantum mechanics. And so in 1926, Erwin Schrödinger proposed the quantum mechanical model of the atom, which focuses on the wave-like properties of the electron. So we cannot know the exact position of the electron, but we can describe the probability of finding an electron in a region of space. And this region of space we're going to learn to call the orbital. And so the Schrödinger equation, developed by Erwin Schrödinger, is an equation that lays out the physical space in which we have a high or low probability of finding an electron. So we have a wave equation that we can solve to create a wave function for an orbital. And the wave function squared can give us the probability of finding the electron within a region of space. So whereas the Bohr model had sort of a classical trajectory of an electron, the Schrödinger quantum mechanical model has a probability distribution map of areas of high probability and low probability of finding an electron. And these areas of probability are called orbitals. So an orbital is a region of space that can be occupied by electron density, or we call these electron clouds. And so we have different types of orbitals that are defined by their relative shape. So the first orbital we'll talk about is called the s orbital. So the s orbitals are spherical in shape, and they penetrate close to the nucleus. So if we look at this orbital here on our x, y, and z planes, we can see that this s orbital is a sphere. Only one s orbital exists per energy level. So if we remember when we talked about our Bohr model and when we talked about the Balmer-Rydberg equation, we have these energy levels 1, 2, 3, 4, 5, 6, etc. that go further and further away from our nucleus. These are the energy levels we're talking about. So for each of those energy levels, there's only one s orbital present for each one. And so the higher energy level that you get, the further it extends from the nucleus. And also, the higher energy level you have, the more radial nodes that you find. So if we take a cross section of a energy level 2 s orbital and then an energy level 3 s orbital, what we see is these concentric spheres. So for our 2s energy level, we have a sphere in the middle, a node, which is an area of 0 probability, and then a larger sphere on the outside. The 3s, we have an inner sphere, then a node, a second sphere, another node, and then a third sphere. So these are all areas of probability of finding a specific electron within this s orbital. Okay, and these nodes are area of 0 probability. So if we think about what these nodes actually mean, so there's an electron that has a certain probability. So this is these graphs here are probability distributions where we're talking about x-axis, which is going to be our physical distance in picometers from the nucleus, and then our y-axis here is the total radial probability of finding the electron. And so you can see we have these three distinct areas for a 3s orbital, three distinct areas of probability for finding an electron. But separating each of those different areas of probability are areas of 0 probability, which mean that this electron has to be able to jump between these areas without actually physically taking up space. So if you think about it too hard, it'll make your head start to thump a little bit. But this is the sort of the world that's a field of chemistry called physical chemistry, where physics and chemistry sort of collide. They focus on this Schrodinger equation quite a bit. So that's the s orbital, which are spheres. Next is the p orbital. So the p orbitals are dumbbell shaped with a nodal plane running through the nucleus. So you can have these p orbitals in the x direction. So there's two different, so think about a barbell. So there's two different areas of probability of finding an electron. You can have our px orbital, which is drawn along the x lines, py orbital drawn along the y, pz orbital drawn along the z axis. So there are three different orientations for these p orbitals. And so these p orbitals exist in energy level 2 and above. And so the higher the energy level, the further this p orbital extends from the nucleus. So the bigger the barbell. Next is the d orbital. So the d orbitals are more complex with two different nodal planes. Okay, so there's 5 different orientations for the d orbital. So you have the d sub xy, where you have an orbital running between the x and y axes, and then one between, so there's one running between the x and y in one orientation, and the other running between the x and y in the other orientation. You have the dyz, where you have the nodes going between the y and z axes in all 4 quadrants. You have the dxz, where it goes between the x and z orbitals, or the x and z axes in all 4 quadrants. You have the dx squared minus y squared, where the orbitals go actually along the axes instead of in between. So all of these xy, yz, and xz all go in between the axes. The x squared minus y squared go along the x and y axis. And then finally, the dz squared is what we call the dumbbell donut, where we have a sort of a p-looking orbital going along the z-axis, and then a sort of donut around. And so d orbitals are found in energy level 3 and above, and the higher energy level that you get, again, the further that d orbital extends from the nucleus. Next, we have F orbitals, which are much more complex with 3 different nodal planes. There are 7 physical orientations of F orbitals, and they're located in the energy level 4 and above. And again, the further out the higher the energy level, the further the, that should be reading F orbitals, the further the F orbitals extend from the nucleus. And so you will not have to draw any of these F orbitals, but you will have to draw the S, P, and D orbitals. Okay, so we'll switch over to the whiteboard here, and I'll show you the proper way to draw each one of these orbitals. Okay, first off, we'll draw the S orbital. So there's only one orientation of an S. So if we draw first we would start off by drawing our axes. We're going to have our Z-axis going straight up. We'll have our X-axis going left to right, and then we'll have our Y-axis going in and out of the board. So for an S orbital, this is simply just a sphere, so you just draw a circle. Next are our P orbitals. So if we're talking our Z, X, Y. So for our PZ orbital, we draw a dumbbell along that Z axis. For the PX orbital, we're going to, so again, Z, Y, X, we draw our dumbbell along our X axis. And for the PY orbital, Z, X, Y, we draw our dumbbell along our Y orbital. So you will be responsible for drawing all of these orbitals. So I would practice this. Okay, so we have our S orbital, and then we have our 3 different P orbitals. Next will be our D orbitals. Okay, so our D orbital, so I guess this should be, a lowercase d. Okay, so get all of my axes drawn. Okay, so Z, X, Y. Okay, so if we're talking about Z sub X, Y, what we have are nodes in between the X and Y axis. Okay, in all 4 quadrants. D sub XZ, we draw nodes, or we draw our dumbbells in between the X and Z axis. DYZ, we're drawing our dumbbells between the Y and Z axes. Our dx squared minus y squared, we draw them along the x and y axes. And then we are our dz squared, we draw a dumbbell along our z axis, and then we draw a donut along the xy. All right, again, you will be responsible for drawing all of these different orbitals. So I'm not looking for a beautiful drawing, but I'm looking for a very clear drawing where I can see where each of those orbitals are residing. Okay, so we have these S, P, D, and F orbitals. So you picture the nucleus in the middle, and then all of these orbitals, which again are areas of probability, so areas of spatial probability of finding an electron. And so these orbitals all arrange themselves around the nucleus. So what you get is this dense nucleus in the middle, and then this empty space, basically, with all of these areas of probability of finding an electron. And so these energy orbitals, it really does look like a cloud, a spherical cloud that composes an atom. And so if you take a look at these probability distributions, if we go back a few slides and take a look at these distributions, they come to an asymptote here at the end. So they never actually totally reach 0. So if we think about the outer boundary of an atom, there's no actual specific outer boundary. It comes to an asymptote of physical probability of where to find an electron, but it actually kind of extends forever. Again, another one of the things that makes your brain kind of start to hurt if you think too much about it. So we can explain these different orbitals using a concept called quantum numbers. So each individual orbital, our s orbitals, our 3 different p orbitals, our 5 different d orbitals, our f orbitals, at each specific energy level can be described by these quantum numbers. So the quantum numbers are basically just a code for classification. Okay, so a lot of people I notice a lot of students get really hung up on quantum numbers, and they think it's something really, they hear quantum mechanics, quantum numbers, and they get really scared. It's really not that difficult. It's a classification that I will actually draw an analogy to, very similar to like where your room in a dorm is. Okay, so it's basically an address for each different orbital. Okay, and so it's really quite a simple process. And so the quantum numbers we're going to cover today are the principal quantum number, which has a symbol of N, the angular momentum quantum number, which has a symbol of L, and the magnetic quantum number, which is a symbol of M sub L, so subscript L. First off, the principal quantum number. So the principal quantum number, again, n, is a positive integer, so n is equal to 1, 2, 3, 4, etc. And so this describes the energy level and size of the orbital. So if we're thinking about the Bohr model of the atom, these are the concentric lines going out. So this is the energy level associated with each type of orbital. So this energy level is also often called the shell. And as the value of the energy level increases, the energy of the electron in the orbital also increases. And then the distance of the electron from the nucleus also increases. So in my sort of analogy here of using this code to identify where your bed is in a dorm, you can think of the energy level as which is your dorm building. Okay, if you have multiple different dorms and you're saying I live in this dorm. Okay, so the principal quantum number is your dorm. Okay, the analogy will come a little clearer as we introduce the other components. Next is the angular momentum quantum number, which is L. So the angular momentum quantum number defines what type of orbital, whether it's an s orbital, a p orbital, a d, or an f orbital that we're talking about, by using a positive integer value beginning at 0. So where we have L equals 0 is code for an s orbital. L equals to 1 is code for a p orbital. L is equal to 2 is code for a d orbital. And L equals to 3 is code for an f orbital. There are n different orbital types for each energy level. Okay, so remember n is a positive integer starting at 1. So we have energy level 1, 2, 3, 4 correspond to n equals to 1, 2, 3, and 4. So if n is equal to 1, then there's only one possible angular momentum quantum number. So then L has to equal 0. Okay, and that corresponds to an s orbital. So the n equals 1 energy level only has an s orbital. N equals to 2 means that there are 2 different angular momentum quantum numbers, 2 different types of orbitals. And so we know energy level 2 has a 0 and a 1 for s orbital and p orbital. N equals to 3 means that there are 3 different types of orbitals. So we have L equals to 0, so there is a 3s orbital. L can be equal to 1, so there's 3p orbital. Or L is equal to 2, meaning that there's a 3d orbital. And so this angular momentum quantum number is often called the subshell. So talking about what type of orbital. And so back to our dorm analogy, if the energy level, the principal quantum number, is your specific dorm building, your angular momentum quantum number would talk about which floor within the dorm. Are you in floor number 2, floor number 3, floor number 4? Which floor are you in? Next is the magnetic quantum number. The magnetic quantum number M sub L. And so this defines which specific suborbital that you are in. So we know for the s orbital, there's just the s orbital, that's it. But for the p, we have 3 separate p orbitals, px, py, and pz. And there's 5 different d orbitals, okay, each defined by their own naming. And so the magnetic quantum number tells you which one of these suborbitals are you actually talking about. So it's the code for each specific orbital. So there are 2l plus 1 values for m sub l. And so these are positive or negative integer values ranging from negative L to positive L. So if L is equal to 0, then m sub L is just equal to 0. Okay, so that codes to the 1s orbital that you have. If L is equal to 1, then m sub L can equal negative 1, 0, or positive 1. Okay, so that corresponds to negative 1 is p sub x, 0, p sub y, plus 1, p sub z. Okay, so it's strictly just telling you which one of these p orbitals are you about. All right, if L is equal to 2, that means we're talking about d orbitals. That means that m sub L can be negative 2, negative 1, 0, plus 1, or plus 2. So that simply is saying which one of these d orbitals are we talking about. Negative 2 means d sub xy, negative 1 says d sub yz, 0 means d sub xz, plus 1 means d sub x squared minus y squared, or plus 2 means d sub z squared. So it's just talking about which one of these d orbitals are we talking about. And so if we go back to our analogy, if the principal quantum number was which dorm are you in, the angular momentum quantum number was which floor, the magnetic quantum number says which specific room on your floor is your room. Okay, so it's a code that defines your specific location, or the specific location of an orbital. It's that easy. So this is a table here that defines the specific magnetic quantum numbers that are allowed for each different energy level. So that leads us now to the orbital energy diagram. So orbitals increase in energy as the shell number increases. So as we increase our shell, we get further from the nucleus. And so that being those orbitals being further from the nucleus means that we're in higher energy. And we've seen a plot like this before. When we talked about the Balmer-Rydberg equation, talking about electrons moving from lower energy states to higher energy states and back and forth, we drew plots that kind of look like this. But instead of having each different orbital type, our s orbitals, our p orbitals, our d orbitals, and then the suborbitals, the p sub x, p sub y, p sub z, etc., we just called it energy level 1, energy level 2, energy level 3. Okay, so we're adding more complexity to the story that we introduced to you in the last lecture. Okay, so it's exactly the same thing where we have our y-axis is talking about energy. Okay, so what we have here is as we go to higher energy states, we can see that the energy goes up because we're talking about orbitals that are further away from our positively charged nucleus. So any orbital that is at the same energy level are what we call degenerate orbitals. And so degenerate orbitals mean orbitals that have the same energy level. For example, the 3p orbitals in a given subshell, so if we look at these 3p orbitals, they're all at that same energy. So these are all considered degenerate energy states. And so in this sort of drawing, this is actually the energy diagram for a hydrogen atom. We can see that the 2s and 2p are exactly at the same energy, which means that all of these guys are actually degenerate energy orbitals. And we're going to find out later on that 2 electrons are going to occupy each of these different suborbitals. So we can have 2 electrons in our 1s, we can have 2 electrons in our 2s, and then we have these 3 suborbitals for this 2p, the 2px, 2py, and 2pz. Each one of these can take 2 electrons as well. So we can have, in this energy level 2, we can have 2, 4, 6, 8 electrons in this energy level 2. Energy level 3, we can put 2 in each one of these suborbitals, so we can have 2, 4, 6, 8, 10, 12, 14, 16, 18 in that energy level 3. Okay, we'll get more into that electron packing, I believe, in next lecture. So together, these 3 quantum numbers, our angular momentum quantum number, our principal quantum number, our angular momentum quantum number, and our magnetic quantum number, can describe every single orbital within an atom. Okay, so basically we're saying which dorm building you're in, which dorm floor, and which dorm room. We can assign each one of these different suborbitals by their quantum numbers. So I ask you to pause the video here and assign quantum numbers to each of these circled suborbitals. Okay, and we'll go through and work through this together. So if we're drawing this diagram here, so we have our 1s, 2s, these guys are the 2p, and then we have our 3s, 3p, and 1, 2, 3, 4, 5, 3d. Okay, so if we're looking at this orbital, we're looking at this orbital, this orbital, this orbital, and this one. So if we're writing out the quantum numbers for each, it becomes quite easy actually. So here, our magnetic quantum number, our principal quantum number is simply the energy level that the one is located. So our n here is going to be equal to 1, because we're energy level 1. Our angular momentum quantum number, since this is an s orbital, that's going to be equal to 0. And our m sub l will also be equal to 0 because there's only one option. So that is the quantum numbers that describe this position. So you can either write them out like that, or you could just write them with commas in between, 1, 0, 0. That describes the quantum numbers for that orbital. If we're doing this guy here, our n will be equal to 2 because we're talking energy level 2. Our L would be equal to 1 because we're talking about a p orbital. And then our m sub l, you technically could put any one. You could call this orbital -1, 0, or +1. They would all be correct answers. But really, to make it easiest, in order that you draw them here, -1, 0, and +1, so I'm just going to call that guy 0. But you could technically put -1 or +1 as an answer, and they would all be correct. Okay, so the naming does not specifically matter. This guy here, we have n is equal to 3 because it's an energy level 3. Our L is equal to 0 because it's an s orbital. So therefore, our m sub l would be equal to 0 as well. This guy here, energy level 3. Our L is going to be equal to a 2 because it's a d orbital. And then m sub l, again, we go from -2, -1, 0, +1, +2. But really, we can name these in any order that we want. So really, any of those answers would be correct. But we'll just call that -2 just to make it easy. And then for this guy, at the end, n is equal to 3 again because we're energy level 3. L is equal to 2 because it's a d orbital. And m sub l, we'll call that guy +2. Okay, again, that could be any possible answer. But if you have to answer two different orbitals, suborbitals in the same degenerate orbital grouping, you need to make sure that these m sub l values are different from each other. Okay, so that easy. It's just about assigning physical, like a code position for each of the different orbitals. Okay, so if we take a look at the orbital energy diagrams for hydrogen versus all of the other atoms, so all the other atoms except for hydrogen have multiple electrons, we can see that there's actually a difference in the way that the energy diagrams are designed. So the hydrogen atom, we can see all of the different orbital types, the s orbitals, the p orbitals, d orbitals, etc., are all degenerate, meaning that they're all at that same energy level. Whereas for the multi-electron atom, you can see that all of the energy levels are staggered. So the only degenerate orbitals that we see are the ones that are within a specific suborbital type. So all the 2p's are degenerate, all the 3p's are degenerate, all the 3d's are degenerate, but they're not degenerate with the other orbital types. So splitting of these energy levels in a multi-electron atom is due to shielding, which is a factor of caused by effective nuclear charge, and penetration. Okay, so we'll get into the shielding and penetration in just a moment. But first off, I want to draw on the board the setup for the hydrogen atom and the multi-electrode atom. or multi-electron atom, you are going to have to draw these diagrams for me. So I want to draw it on the board just so you can see how easy it is to draw. Okay, so for the hydrogen, this one's quite easy. You start off with your 1s orbital, jump up to your 2s, and then 3 degenerate orbitals for your, this is our 2p. And then a smaller jump up for our 3s, 3p, 3d. Okay, and then you can draw, etc., up from there. That's for the hydrogen atom. Okay, all of these are degenerate. Whereas a multi-electron atom multi-electron atom is basically every atom except for hydrogen. You start off with our 1s, you jump up to your 2s, and then you step up just a little bit to your 1, 2, 3 for your 2p. So there's a slight energy difference between the two. And then you jump up now to your 3s, then up to your 1, 2, 3, 3p. And this is the part where it could get a little confusing for some people. Before we get actually to our 1, 2, 3, 4, 5, to our 3d, the next in energy is actually the 4s. The 4s is at a lower energy level than the 3d. That's the very important part. And then you can go up to the 4p, which is above the 3d. Okay, as we learn more about filling electrons, you're actually going to be able to tell this very easily by looking at the periodic table. But the order of these, going from 3s to 3p to 4s to 3d, that's a very important thing that you're going to have to remember. All right, you will have to do that on tests and quizzes. Okay, so that's drawing for the multi-electron atom. All right, so let's take a look at the factors that cause this staggering in the multi-electron atom. So the first is effective nuclear charge. So there are a few key concepts in general chemistry that keep coming back over and over again that are kind of landmark, or not landmark, kind of hallmark topics. And effective nuclear charge is definitely one of those hallmark topics. And so effective nuclear charge has a symbol of Z sub EFF. Okay, so Z is effective nuclear charge. And it's defined as the nuclear charge actually felt by an electron. Okay, so if we think about the setup of an atom, we have a positively charged nucleus, and we have these negatively charged electrons that are surrounding the nucleus in these areas of probability that we call orbitals. And so there's an electrostatic attraction between the positively charged nucleus and these negatively charged electrons. So the nucleus is pulling these guys in. But you have to remember, we have different energy levels of electrons, which means you have different layers of electrons that are building up within the atom. And so all of these electrons are negatively charged. So an electron that's located in energy level 1 is going to be repelling electrons that are in energy level 2. Just the same as electron in energy level 1 would repel electrons in energy level 3. Okay? Like charges repel, opposite charges attract. So what we have here is this sort of competing set of attraction and repulsion. So we have attraction to the nucleus and repulsion from our what we call core electrons. So the electrons that are in the way between the outermost electron and the nucleus. And so the effective nuclear charge basically says, what is the overall attraction felt by the outermost electron by this positively charged nucleus? And so the equation for that, the effective nuclear charge, is equal to the Z actual minus the electron shielding. Okay? And so the Z actual is the nuclear charge. So that's the number of protons. So that's telling me how much positive charge in the nucleus do I have pulling those electrons. Okay, so this is talking about how much positive charge you have. And then the electron shielding is equal to the number of electrons between the nucleus and the electron in question. So we call those core electrons. Okay, so if we think about, so if we go up to the board and we think about an atom that has 12 different electrons. Okay, so that would be magnesium. So magnesium has 12 electrons, it has 12 protons. So we have 12 positive charge here that's going to be pulling in electrons. So the first energy level takes 2 electrons. We'll get to this more in the next lecture, but take my word for it for now. 2 electrons in our n equals 1 energy level. There's 8, 2, 3, 4, 5, 6, 7, 8 electrons in n equals 2. And now in n equals 3 energy level, we're going to have just 2 electrons. And so if we add that up, 2 plus 8 equals to 10, plus 2 is equal to 12. So there's 12 electrons in magnesium. If we're trying to determine the effective nuclear charge, we're trying to see how much attraction is actually being felt by these outermost electrons by this nucleus. So the equation here, the Z effective, is equal to our Z actual minus the shielding. Or really, what I think is a better way to write this, Z effective is equal to our positive charge minus the core electrons. Okay, so you're getting an attraction from our 12 protons here in our nucleus, but you're also getting repulsion from all of these core electrons. All of these guys are repelling that outermost electron. So if we can define our different electrons in different orbitals, the outermost electrons in the outermost orbital are called valence electrons. Okay, so here, let me write that up here. Valence electrons are electrons in the outermost orbital. Outermost occupied orbital. Okay, valence electrons are electrons in the outermost occupied orbital. Okay, so down here on the bottom, we'll define core electrons are defined as electrons that are in an interior occupied orbital. / energy level. Okay, so our valence energy level is n equals 3. So our energy level 3 is where our valence electrons are located. Our core energy levels are n equals to 1 and n equals to 2. And our core electrons are all the electrons located in n equals 1 and n equals 2. So for Z effective is going to be equal to our positive charge, which we have 12 protons here, so that's 12, minus our core electrons, which are all the electrons that are not in the valence shell. So our n equals 1, we have 2. N equals 2, we have 8. So 2 plus 8 equals 10. So our effective nuclear charge is equal to 2. So what that means is all of the electrons in the outermost valence shell are feeling a +2 attraction towards the nucleus. There is no shielding by electrons that are in that same valence shell. So even though there are 2 electrons here in this same valence shell, they are not shielding each other. they are both being attracted by a +2 force. Okay, so if we moved over to aluminum now, if we took an aluminum has an atomic number of 13, which means that there's 13 plus in the nucleus. N equals 1, N equals 2, N equals 3. So we have 2 electrons here. 1, 2, 3, 4, 5, 6, 7, 8, and then 1, 2, 3. And N equals 3. If we calculate Z effective, the effective nuclear charge for aluminum, it's going to be equal to our positive charge, so it's going to be 13, minus our core electrons, which again is going to be 2 plus 8 is going to be 10. So that means that our Z effective for aluminum is +3, which means that there is a +3 attraction now on all of these exterior valence electrons. So each of those electrons are being attracted to the nucleus more strongly than the magnesium. So as we move from the left to the right on the periodic table, what we're going to notice is our effective nuclear charge is going to get larger and larger and larger, which means that that attraction of the outermost electrons are going to be attracted to the nucleus more strongly. So we're going to see that later on that this effective nuclear charge trend going from left to right, having a larger attraction to the nucleus, how it's going to have a big effect on the atomic radius. But what we see here is that the shielding, as we start to fill these lower energy orbitals, it leads to this staggering of each individual suborbital type. So whereas our 2s and 2p orbitals have different energy levels as they start to become occupied with electrons. So the second factor that leads to this staggering is called penetration. And so electrons and orbitals located in closer proximity to the nucleus feel a stronger nuclear attraction, and therefore they have a lower energy. So if we take a look at the probability distribution for a 2s orbital in blue versus a 2p orbital, we can see that there is a higher density closer to the nucleus. So on the far left, so x-axis is distance for the nucleus in angstroms. So we can see the 2s orbital has a probability that's closer to the nucleus, meaning that there can be a stronger attraction to those electrons, meaning that it would appear lower in energy. So the combined effect of effective nuclear charge and penetration are what are leading to this staggering in the multi-electron atom energy. Okay, and so we have these trends now as we go from the s orbital to the f orbital. We're increasing in energy, but we also are accompanied with a decreased attraction to the nucleus due to the effective nuclear charge. So an exercise that I set to you guys is to draw each possible s, p, and d orbital and assign each with the proper set of quantum numbers. Okay, so I'm not going to draw these up on the board in this lecture. I already drew the s, p, and d orbitals for you. You can go back and watch that part of the video and just try to link those up with the energy diagram that I went through, linking all the quantum numbers to each of those different orbitals. So this is very critical for you to work through with this practice exercise. So the last slide that I have for you is just a quick conceptual problem here to state which of the following sets of quantum numbers are allowed. If it is not allowed, explain why. If it is allowed, name and draw the orbital. Okay, so if we take a look at each one of these different opportunities, we can take a look at each and see which ones are allowed. So n equals 1, L equals 1, and m sub L equal to 1. So again, sorry, if you should pause your video and work through this on your own. If you, once you finish working through, then replay and then to listen to these answers. Okay, so this first possibility, A, is not allowed. The reason is, at n equals 1 energy level, the only type of orbital that we have is s. So that corresponds to an L equals to 0. So this L equals to 1 is not allowed. For B, we're taking a look at n equals 3, L is equal to -1, and m sub L is equal to 0. This is not allowed because our angular momentum quantum number is equal to -1. This is only our angular momentum quantum numbers are only positive integers starting with 0. So 0 for S, 1 for P, 2 for D, 3 for F, and so this -1 is not allowed. C, n is equal to 0, L is equal to 0, m sub L is equal to 0. This is not allowed because our energy level cannot be 0. Our principal quantum number cannot be 0. D, n is equal to 2, L is equal to 0, m sub L is equal to 1. Now this is not allowed because so we have a 2s orbital, but an m sub L is equal to 1 is not allowed. The only m sub L possible for the s orbital is a 0. So E, n equals to 3, L is equal to 1, and m sub L is equal to -1. This is allowed. So this is talking about a 3p orbital. And then so we have px, py, and pz. M sub L of -1 is just talking about one of those 3 suborbitals. So E is allowed. All right, with it, that's it for the day.